It is our great honor to welcome our speaker, Mr. Craig McDonald, Business Line MD, Industries at ABB Robotics. Mr. Craig McDonald will share his insights titled Industrial Grade Physical AI for Robotics. Ladies and gentlemen, please welcome Mr. Craig McDonald.
Yay. Thank you very much. Ah, really great to be here, everybody. So I have the honor of running a business called Robot Industries within ABB Robotics. And within that, it's actually great to be here at Computex. And just the mere fact you've got an industrial manufacturer like ABB at an event like this just shows how the importance of compute and physical AI are really merging together with the technologies that we build. And we're going to an incredibly exciting era here that I'm looking forward to sharing our insights and how we're approaching it. So, okay, there we are. So ABB is a business that's been around a long time. In 1974, we were the first company to use microprocessor controls with a robot and essentially invented the modern industrial robot. And over the next 50 years, we've built that out into a very broad portfolio of industrial robots, of collaborative robots, as well as mobile robotics. There's over 1,000 different instances of different robots that we make as a company today. And we've subsequently evolved that further. We haven't stopped just at the robot instance, but we're also now moving to a world where we're adding intelligent eyes, where we're adding hands, and where we're adding a brain to these robots to allow them to operate more autonomously and in a more versatile manner. And this is changing where robots are being used. Our heritage started off in automotive on these highly standardized production lines. And you're now starting to see robotics move out of those traditional spaces into the more high-mix, low-volume spaces like logistics, like service robotics, like lab automation. All of these that demand this autonomy and this versatility if they're going to be able to effectively operate. But we're not stopping there, because a lot of this requires deployment with industrial grade quality, with the reliability that you get a product, you know it's going to work. And for all these technologies to really come together, you need to generate this industrial grade capability. And you need to pull this autonomy and versatility together at a point where you can simulate it, where you can then create detailed simulations that can then drive the performance of these products in these varying industrial environments. And that's really where the next step is going as we continue to evolve our product range. Now, imagine a robot that can see its environment, it can understand that environment. So it knows that it might be moving amongst people, it might be moving up to a wall, an industrial plant. And of course, how you behave in that environment changes consistently in each of these different situations. And we've built a suite of technologies over the last 20 years, actually, this has been going some time, that when they all come together can add that intelligence to the overall robot performance. So think about a robot moving freely around a logistics environment, moving autonomously, not requiring human intervention. Or think about a robot that before used to do just a single application, but now can do multiple different applications with that same robot. This autonomous behavior, this versatility, is something that is happening and is happening at scale right now. But what we need as we move to the next level here is to move beyond just the technology. We need to now be able to look at how this is going to operate and how the suite of technologies come together and make intelligent decisions on then how to behave. Because the world is not standard. The person will move. Somebody will leave a rack of boxes in the way of the robot. You might be in a production environment that is so incredibly variable, like this room, where these lights might go out. Traditional robot systems would then shut down and wouldn't be able to continue to operate. But if we could simulate all of that and build deep, physically accurate simulated systems, we can actually manage those variations. And that's really where the next step of this robotic approach is going. Now, we started a few months back. We announced in March a deep collaboration with NVIDIA. And we looked at bringing together the capabilities across the industry here, where you take a company like ABB, with obviously the deep roots in the robot technology, in the motion control with that technology, but also our Robot Studio digital twin. And we've spent many years developing this digital twin capability. And you complement that with NVIDIA's capability on accelerated compute, and you complement that with the deep understanding around the simulation and the synthetic data side, and you bring those two capabilities together. And why this is incredibly important is, up until now, synthetic data has not been accurate enough to safely control a robot. Being 80% accurate isn't good enough. We're talking about people safety here in many instances. And if you're not getting accurate synthetic data, you can't pre-train your robot systems, so the simulation in many cases still relies on deep on-site commissioning, deep on-site training. Now imagine, and we've started to achieve this in some areas, especially in the electronic space, imagine if you could make that synthetic data physically accurate to the point where the robot path generated virtually is 99% correlated to that robot path that occurs in real life. You no longer even need to have real parts. You can, in a completely virtual environment, pre-train your robot systems so that they can be ready for whatever variability throws at them. Now, this change has happened very, very recently, and it's certainly one that we're incredibly excited about because it is going to change the way we approach our robot systems. And practically, it realizes itself in this product that you see behind me, which is our Robot Studio Hyper Reality product. Now, imagine a situation where you don't have a part at all. What you've got is just a design. And you start from that actual design of a product, and then you recreate it synthetically to a very, very high degree of accuracy. But you don't stop there. You also then create a vision digital twin of that product that can then be trained with the synthetic version of the product that you've just created, so that our simulation sees exactly the same scenario that a robot would be seeing in real world. And then you take that and you add that to an AI model that you can then train, and you do this for many, many different variations of that product. So think of different positions where somebody might present a product to a robot, different orientations, simple things like that. Think of more complicated situations of where you might have a fashion clothing line with variations coming at you that aren't always exactly the same and not completely predictable. You can now learn and place learning systems around scenarios developed in the virtual world to be able to handle this variation. And that's this Robot Studio Hyper Reality. Now, let's turn that into a context of, we're standing here in Taiwan with Computex right now. We're in a bit of a super cycle in electronics. It's a very exciting time. But it's also an industry that is getting more and more complicated by the moment. So maybe just a few years ago, it might have been products designed in Taiwan or designed in China and manufactured in China with a very short and quite simple supply chain. Maybe you only updated the products every 3 to 5 years. That's changing quickly right now. You're probably sitting in Taiwan right now. You've got a factory in China. You have another one in Vietnam. You've maybe got another one in India. And you've even got aspirations to make this thing in North America. Many places with varying levels of robot and automation capability, but a very extended supply chain that can be extremely variable. So the complexity just went up many-fold. But you're also facing a situation of where every 1 year to every 3 years, you've now got to come out with your new consumer electronics product. You've got to be so much quicker. And of course, consumers are asking for many, many different variations. So you end up with this exploding complexity that is maybe not at anywhere near the same level as what you perhaps faced just 5 years ago in this industry. So what do? Well, traditionally, you would have approached this from a basic rules-based automation architecture. You would have tried to control the environment. You would have tried to make sure that every factory looks exactly the same. You would have made sure that the lighting conditions were identical. You would have really worked and beaten up your supply chain to make sure that tolerances were absolutely precise all the time. And then you'd put a standard automation and maybe a robot production line there that would work very, very well if everything was perfectly controlled. Now with this variability, that line is probably struggling. That line is probably now seeing downtimes accelerate. It's seeing situations of where they may not have the right kind of labor immediately available to it to be able to keep the line and keeping those conditions perfectly stable. So what do? You move maybe more to an adaptive data-driven design where instead of fighting these variations, you embrace these variations. I think if we're going to be able to make productive robotic systems that are globally scalable at an industrial scale, I think we've got to embrace the fact that these conditions are not always controllable, and we need our systems to be adaptive to those variations. We need to be able to have an automation line that will immediately recognize a certain scenario because it's been pre-trained in the digital world, and then adapt its automation to that digital situation. But you also then need to complement that scenario, that synthetic data, with the real-world data as you continue to optimize these AI models that you perform in. And therefore, you can then handle this adaptive nature of these different environments and the variability. So maybe you're an electronics manufacturer here, and traditionally you started your production line development when you got that actual product. I mean, for those of you who are very familiar with the consumer electronics space, that's a very highly guarded secret quite often, and you don't get that product until very late in the development cycle. And then you've really got to race to get your production line ready. If you pre-simulate this in the synthetic environment, you can, in a dynamic way, work in parallel now to the engineers developing the actual product that you're going to produce. You don't start when the product is finished. You start when they start developing the product. And then you can then dynamically update the synthetic version of the product, and therefore then set up your production lines and pre-train all your production systems so that you're working in parallel. Sounds trivial. I mean, the dream of concurrent engineering has been out there for a long time. But to do this in the electronics environment can probably see a halving of time to market of many of these systems. Then when you get into actual production, we traditionally would then spend a few months going through a commissioning phase. So we would check all the different variations, we would fine-tune all the designs that we had done off-site when we get on-site. But now if you've got a perfect digital twin of that product with this high-fidelity synthetic data, and we're able to, within, say, an NVIDIA world model environment, map all these different variations out, we can pre-train that system before we get to site, so that after 1 week of production, you're at the productivity levels that you normally would have expected only 5 to 6 months into production. So you immediately get up to this point of productivity. So these are very real problems that people face day to day. But if you had the right level of synthetic data and simulation, you could really change the way we approach this. So we've this March, announced this collaboration with NVIDIA, where we brought together NVIDIA's accelerated compute with NVIDIA's simulation strengths, and we combined that with our industrial knowledge, our digital twins, and our obviously wide range of robotic capability. And we've now moved to the point where we, with this 99% accuracy on the synthetic data, can build these very detailed digital twins up in advance. And we can, on the video behind me, we can then map different light conditions, different part tolerances, and material variabilities, so that these are all pre-trained, so that by the time that product hits the shop floor, the part behind is ready with every single light condition, every single variation, and you can immediately hit full productivity on your production line. So what you see behind me now is an actual application going and operating right now. We've worked closely with NVIDIA on the development of the concept, and we've also worked now with Foxconn, where you see behind me an electronic part being assembled. Now, the picture on your right-hand side is the digital simulation of that using high-fidelity synthetic data. And the image on the left-hand side over here is the actual system in operation. Now, some things that we learned as we went through this first installation. We were able, obviously, to develop the full automation system without having the actual part. And these are very, very small parts. You know, there might be just a little button on the side of a device with some very small spring configurations to make that button operate. But on our traditional system, we probably would have had to have 5 cameras looking at this, and then still struggle to be able to see exactly where that part was or where our robot was on the vision feedback system. But if you've got a high-fidelity synthetic data, you can probably get by with just 1 or 2 cameras, and you regenerate the rest of the detail of that part using the synthetic data. So you can then much more accurately determine where you're going to grip that part and how you're going to make sure that you can very reliably manipulate that part into the position and then operate it. And of course, you see in the back there, you've got some lights in the factory. Well, on Monday, one of those lights fails. You shouldn't have any impact on your production system. We pre-trained this system with many different light environments within NVIDIA world model to then be able to be ready for that with a specific robot scenario that can immediately take over, and then you continue to drive your efficiency. So this is operating now, and it's moving at pace as we have a deep collaboration between the teams as we pull these technologies together. But it's if you look more widely, this can be transformative to the industry. You're looking at cutting setup times 80%. I mentioned it might take many months for us to get systems set up. There's a lot of trial and error. But if you pre-train for this, really, within the first week, you should be up and running. You look at reduction of time to market. I spoke about the concurrent engineering. The need to maintain confidentiality of parts before you go into production and how they can be tightly controlled. But if you can work with really deep synthetic data variants of this, you don't need the part. You start from immediately the point at which the engineering team starts developing that part. You don't wait to do your production system right at the end. And then, of course, on the cost side here, I mentioned fewer cameras. I mentioned more reliable connectivity. So our throughput and our yield of these production systems really does improve significantly. So you put this together, and the intelligent use of physical AI, embracing this variation, can make a fundamental difference to your business model and the productivity and profitability of the application that you put out there. So with that, we've moved from the world of manipulators, we've moved to the world of autonomous, versatile robotics, and we're now pulling that together inside a simulation environment that's launching this September, where we hope to then move to the next stage of this industrial-grade physical AI adoption to reliably deploy these systems at scale across the world. So looking forward to it. Thank you, everybody.